So here we go. What we'll do now is Ampere's laws applications. So, or rather, applications of Ampere's law. And you will see that for some specific problems that have nice symmetry, Ampere's law is easier to use than Biot-Savarad's law. Biot-Savarad's law in principle always works. Ampere's law works only for select few problems that have a nice symmetry. And so we will go over these problems here. I think there are 4 problems that you need to know how to do. So here's the first one, and this is on your worksheet. So what it says is, using Ampere's law, derive expression for the magnetic field of a long straight current carrying wire. We already did this with the Biot-Savarad's law, and we got this answer here. It took some work. It wasn't necessarily easy, but it wasn't all that complicated. I don't think so. Still, this is going to be even easier. So let's state Ampere's law. What we have is an integral of b dot dl. And this is the integral that we, it's a line integral that we perform over some loop, some closed loop. I'm going to put this loop in the red here. And this is equal to mu naught times I enclosed. And this current has to be enclosed by this loop along which we integrate. So this is the law. Now let's see how this works out for our picture here. So in 3D, the picture we have is that there's a wire here, and then there's a certain current that flows through this. So here's I. And then using right-hand rule, if you use right-hand rule, you can determine the direction of the magnetic field. So take the thumb of your right hand, put it on this wire in the direction in which the current flows, and then curl your fingers. And when you do that, you will find out that, so your thumb points in this direction. And when you curl your fingers, you will see that you get a magnetic field that does the following. Right, so it curls like this. This would be the magnetic field around the wire. And of course, if you move farther out, you would still have magnetic field, right? Just a little farther out and it would be weaker. If you move closer towards the towards the wire, you would still have the magnetic field, but it would be stronger. It would still curl the same way. So between these lines of the magnetic field, you have more lines of the magnetic field. The magnetic field takes up the whole space here. Now in 2D, your picture would look like this. So the current comes at my face, and so I would draw it like this. That and let me put it somewhere else because I think I might need a bigger picture. So here's a that. Here's the actual current I. This is a symbol of something coming at me out of the page, right? Remember that we have this little convention here that this means out of the page, and this means X means into the page. It's as if an arrow was coming at you, and then here it's as if arrow was going away from you into the page. All right, so we have a current here that comes at me, comes out of the page and comes towards me, and then the magnetic field would do this. This would be the magnetic field, just goes around like this. Circular, and it just points like this. This is B. Now in reality, if I were to really draw this properly, I should draw this magnetic field like this. And then this thing just loops around, and so the magnetic field is tangential to the circle everywhere here. Here's your magnetic field, and this is what it does. It has the same magnitude at every point along this circle. So the magnitude stays the same. So let me put this here on the bottom. The magnitude of B stays the same, so B is constant. But the direction of the magnetic field does not stay the same, and therefore the vector B is not constant. Right, magnitude stays the same, but the direction doesn't. Alright, so we have that. Now, what we need is a loop. So here I need to integrate this thing along I need to integrate the magnetic field along a certain specific loop, and so what I'm going to do is, here's the loop that I'm going to choose. I'm just going to put it right here. And I'll go around in a circle along the magnetic field. Now in principle I could choose any loop I want to. But I want to be clever about what loop I choose, and you'll see why this loop makes sense. Hopefully you see by now that it makes sense to choose this loop. Here's a little dl. At another point, here's dl. At another point, here's dl. Maybe I'll draw one more, maybe somewhere here. Here is another dl. Now from the picture here, it should be clear that dl, the vector dl, this little element of the length, is always perpendicular to the magnetic field B. I'm sorry, it's parallel. The two are always parallel. And so now what I can do is I can take this equation and I can, well, I can rewrite this like this. So the integral of B dl cosine of 0, right? B and dl are parallel, and therefore the dot product with the cosine would just be cosine of 0 equals. I still have to integrate this along the closed loop, so I'm going to put that in here. Mu naught times I, just I, because here in this case, I enclosed is simply I. The only current here that is enclosed by this loop is just this current I. Cosine of 0 is 1, so what I end up with is B dl equals mu naught times I. Now B is constant, the magnitude of B is constant. We already put this thing here. So I can pull this out of the integral. Let me just add this little loop here. So B, the integral of dl equals mu naught times I. Here I'm doing this integral along the whole loop. I add all of the little elements dl. When I add up all of these little elements dl, then what I get is, well, let me keep this loop here. When I add up all of these little elements dl, then what I get is simply the whole length of the path. And so this is what I get, but the whole length of the path is nothing but 2 pi times r, where r is the distance from the center to my loop. All right, now that I have this, the magnetic field becomes mu naught times I over 2 pi r, and that does it. So this was a lot simpler, I think, than Biot-Savart, but all right, so here's the first application. Now let's move on to the next application of the Ampere's law. That is actually, so the next one is more complex than this one. This one was almost, well, this one was easy compared to the next one. All right, so here's a harder problem where we will use the Ampere's law to find an expression for the magnetic field produced by a current. So what we have is, well, we have this wire here, but we no longer simplify it as just being very, very thin. Rather, we want to account for the thickness of the wire. And so there is some radius r that this wire now has, and then the current I flows through this. And the question is, this current I, what field does it set up on the inside of this wire? And then by extension, what field does it set up on the outside of this wire? This is what we're looking for. And we already know one of the answers. The magnetic field on the outside of this wire should be this. We just solved that a minute ago. So the magnetic field outside of the wire should be this, and hopefully we'll get there in a few minutes. So let's consider first the well, let's state the law. Let's state the Ampere's law. So what we have is B dot dl equals mu naught times I enclosed, and this is a line integral along a closed path. So what we need to do here is draw a picture where you have a bunch of charges here, and these charges flow with the current. So this would be in 3D. In 2D, if I were to draw it, now we're going to need a bigger picture for 2D. Let's see. Maybe I can, let's just put it here. So 2D. So here's the big circle. Not bad. And we have all of these little charges that flow into the page. So I'm going to put little x's here and here and here, and all of these little x's will indicate some sort of a current that flows into the page within the wire. And then I'm just putting some x's, but there's a current that flows everywhere here into the page. So this is all of these little currents here. And here's the center. This thing has a radius r, so let's put this in the picture. This r. And I want to figure out the magnetic field on the inside here. Now, it's not an unreasonable guess that the magnetic field should still be circular, because if I take my right hand and I point the thumb in the direction of the flow of charges, then I curl my fingers, then I should end up with some sort of a circular field. It's just that I have so many charges that flow, so all of them would add up into something. But it's not unreasonable to suspect that it would still be circular. So maybe I'll draw a field at some arbitrary location within. Let's say here. Now, if I use the right hand, then the magnetic field should point in this direction and then going. So this would be the magnetic field on the inside. Right, so this is B. And I set it up at some distance, at some radius r, little r, away from the center. So that what I have here is little r is less than big R. Right, now what I need is, so I have determined more or less the shape of the magnetic field. I can also add something to it. That is, this will sort of carry from the previous problem, but the magnitude of the magnetic field, it seems to be sort of obvious. I don't think it's actually obvious, but it seems to be sort of obvious that the magnitude of the magnetic field stays constant wherever I drew it here along this circle. And if I move farther out, the magnitude of that field would then change. If I move closer towards the center, the magnitude of that field would change. But along this path here, along the circular path, the magnetic field should have the same value. Now, of course, it changes the direction, and so the vector B is not constant, so keep that in mind, but we have this. All right, so I figured out the magnetic field. I figured out this B here in the equation. Now I have to figure out the element dl. I have to choose some path along which I want to integrate this magnetic field. And, well, I could choose any path whatsoever, so I could choose some random path that looks like this if I wanted to. As long as it closes, as long as it's a closed path, that would work. But you know, but that would, you know, that wouldn't help me much. So instead what I'll do is I'm going to choose a path that starts here and stays with the magnetic field, goes all the way around, and then I come back to the same spot. And let's draw a few elements dl. So somewhere here I'm going to have element dl that points like this. Somewhere here I'm going to have element dl that points like this. Somewhere here I will have element dl that points like this, and maybe I'll do one more. There's an element dl that points like this on the top. So I have these dl's here. And from this picture, it should also be clear enough that dl's are parallel to vector b everywhere along this specific path. So with that, I can now start to play around with this equation. So the integral of b dot dl becomes b dl times the cosine of 0, and it's cosine of 0 because dl and b are parallel, equals mu naught times I enclosed. And this is a closed loop. Now b, the magnitude of b is constant. We have set it here. I can pull this b in front of the integral, so what I have is b, and then I have the integral of dl, cosine of 0 is 1, equals mu naught times I enclosed. Now the integral here, the sum of all of the little elements dl along this whole loop is just going to give me the length of the loop. And so I'll have b times l equals mu naught times I enclosed, and l is nothing but 2 pi little r. This would be 2 pi times little r. It's little r, it's not big R, because if I were to put big R here, then I would be calculating the length of this arc, or of this circle. But if I put little r here, then I'm calculating the length of the red loop, and that's what I want. Equals mu naught times I enclosed. So I would almost be ready to be done, but not quite yet. This becomes mu naught over 2 pi times I enclosed over little r. This is good, except that I still have to figure out this I enclosed. See, I enclosed in this picture is just the current that is within the loop, not the current that is outside of the loop. Let me put this here on the side. What I need from here, let's go up, need I enclosed, and then I enclosed is not equal to the total current I. Right, because only some part of the total current flows through this red loop. So let's figure this piece out. Now the equation for the current in general is dq dt, but because we're going to assume that the current through this wire flows at a steady rate, at a constant rate, I'm just going to turn this thing into averages, and then to simplify our life, we will turn this into q over t, where t is time, and q is the charge that flows through the wire. Now because this is if I make this thing total, the total current, then this has to be the total charge. But if I want to use the enclosed current, then that would be Q enclosed over the time instead. And so this is the equation I'm going to move forward with. So what do I do with Q enclosed? Well, you may recall, maybe you don't, but the charge density is Q over volume, right? And in this specific case, we're going to assume that the charge density is constant, that it doesn't vary throughout the wire. So we could say that we have a total, or some total volume of the wire. And so now what I would have is that, well then, since we're going to assume that the density of the charge here is constant, and so that would imply that I could also write Q enclosed over the volume enclosed by the loop. I'm looking at the charge within this loop and the volume within this loop. And so now what I have is that if I combine these two, what I'm going to get is that I enclosed is equal to charge density times volume enclosed divided by t, time. Now volume enclosed times volume enclosed, well that's just going to be, well you have to look at it this way. What you're looking at is a cylinder, whole cylinder. It runs like this. But within the cylinder you have this little loop, and it's that loop here that determines the volume that you're interested in. This here would be the volume enclosed, and that would be pi r squared times some length L, where this is little r, just like this is big R. And then length would be, well, some length L of this volume here that I take, some arbitrary length L. So let's put this here. What I will get therefore is this is pi times r squared times the length. All right, so now that we have this equation and this equation, we can combine the two and see what we get out of the two. So by combining the two, we get the following expression, that the magnetic field on the inside is going to be equal, so I'm going to put here on the inside, is equal to mu naught over 2 pi times, well, let's just copy this thing over. So what I have is rho for the density times pi times r squared times L divided by time times R. Yeah, I think I got all of the pieces. So that takes care of this. And now I'm almost done because the rest is, well, I still have some algebra, but I almost have the expression that I want. So maybe what I'll do is let me move from here all the way to here. And then let's see if we can finish it in this line. Perhaps we can. So the magnetic field on the inside, the wire, now becomes mu naught over 2 pi times, well, pi cancels out, so I can get rid of that. So let me get rid of that as well. Second. So this is over mu naught over 2, and then pi goes, so that goes away, times rho times r over t, where t is time in which the charge would flow through this section here. Because t comes all the way from here. We pulled t all the way in, t shows up all the way here where you have the total charge, or actually from here where you have the enclosed charge that flows through a certain length of the wire there in a certain amount of time. So let's see if we can make a little more sense out of it. What I have here is, oh, that's right, times L. I forgot L. This is what I have. Now, the charge density, it stays the same throughout the whole wire. So I can write that this is Q total divided by the volume of the whole wire, volume total. And so for that reason, this equation now becomes mu naught over 2 times Q. And I'm going to put here total Q over the total volume. And so the total volume would be pi big R squared times big L times, and now I have little r times L over T. All right, so just in case you're wondering what just happened, this thing here, that's this. All right, now L cancels, that's good, so that goes away. And I'm going to rearrange this so that I have mu naught over 2 pi times r over r squared times Q total over T. Now remember that this little t here was the time that it would take for the charge to flow through the length of the wire. And this Q here is the total Q. So this whole expression here, Q total over T, this here, and maybe in blue. So this thing here becomes a current I. Recall this equation. And so now I'm getting close. This gives me, well, actually now I'm done. So the magnetic field on the inside is simply going to be mu naught over 2 pi times r over r squared times I. And let's confirm that this is in fact what we were aiming for. Yeah, okay. Alright, so this was net trivial, that's for sure, but there's that. Now this is the magnetic field on the inside. What we still want to do is determine the magnetic field on the outside. Let me do that part. We have already done that. That is, we've done it a little differently, but now let's see if we can take this equation and figure that piece out. So let's maybe separate this. And I need a picture for this. Well, actually, here's what I could do. So let's say that I want to figure out the magnetic field. I'm looking at this picture here. This is where I am. Let's say that I want to now figure out the magnetic field at some location, at some r away. So this is little r now. This is my r at this point. And r goes from the center of this circle all the way out to this point. And then I'm going to say that this distance here from the surface of the wire to the point of interest, that's d. In other words, r, little r, equals d plus big R. I'm going to use that. I'm going to use this in this part here. Now I'm also going to take this equation and bring it here as well. So on the outside, what I could do is I could take this equation and write B equals mu naught over 2 pi times little r becomes d plus big R over r squared times I. Oh, by the way, this is I total, right? So remember that this was not the enclosed current, but the total current through the wire, times I total. And this becomes mu naught over 2 pi times d over r squared plus 1 over r times total current I equals. All right, now if d is much bigger than r, so d is much bigger than r,